All right, I went ahead and hit the record button there. You may have to agree to that. Um, Welcome, guys. Good to see everybody again. We'll get started here. So first thing I want to tell you is I need to apologize for probably a slow response for those of you that have been contacting me in any way. My Weber State account got hacked. I'm not sure how, but I was unable to log into email, Canvas, like nothing was working.
Well,
And
where are all our A's at?
what's that?
I said, well, where are all our A's at?
I know we got to get to that. So, but it was funny that the tech guy that was helping me, we spent. I had two phone calls. At first, it was like messaging, but I did two phone calls that went for like an hour and a half each. First one, we couldn't figure anything out. It took him over a week to get my account back online. I still don't know what happened, but I apologize for any slow answers. I have a bunch of emails from you guys. I've answered some and tried to correct a few things on tests. But anyway, I'm working on it. So give me a second to kind of catch back up. So I apologize for that. I normally try to be on it a little more than that, and unfortunately that kind of held that back. But second item of kind of business here is the test. It looks like everyone pretty much got to the test. Again, on the test, there were a few questions that a lot of you had. One of those, the one that comes to my mind quickly, is there was a question about radiation traveling in 360 degrees. And it was marked wrong. All of you were right. That said 360 degrees, and I'm working on fixing that. I actually migrated a bunch of the tests from last semester to a new test bank, and somehow some of the answers must have gotten weird. I went over it beforehand, but I didn't notice a few of those, so I'll be checking that. And then the other thing I'm going to do is I had your next test, the test number 3, available today when we end this class. I actually took that off, and I'm going to make it available Monday because I want to go through the next test and make sure there's not any weird things that throws everybody off and creates panic and a bunch of emails. So I'm going to go through that one first before I put it on. So I'll make that one available by Monday. That way I can hopefully go in and make sure there's nothing weird on there that's totally wrong. But for all of you that sent me emails about ones, I'm getting to them, and most of your things are right, which actually made me happy as a teacher, because you were asking questions and saying, hey, this isn't right, and you're correct. So most of what you said on there was right. So, and then there's a few of you that had questions that were unrelated to tests and just general concepts, and I will try to get to those all as soon as I can. So I appreciate your patience, and sorry about the dumb hack. I'm not sure what happened, but anyway, having said all that, we'll kind of get going today. So today we are going to be going over radiation detection equipment. And so last time we covered gamma camera, and this time we're going to kind of cover some of the other instruments and things that we use today. And then at the end of this lecture, we're also going to have a brief discussion. Hopefully it will be brief, on statistics and why we use statistics in nuclear medicine. So let me get my PowerPoints pulled up, and then we'll get started. I'm going to move you guys to my other screen. Okay, can you guys see my slides? Yes, okay. Make sure I got the window where I want it. Okay, and you guys can't see anything but my slides, right? Okay, perfect. All right, so like I said, we're going to go over radiation detection equipment. I've included a few slides at the beginning that are going to be slides that match the previous lecture. And you probably noticed that if you looked at the slides already, or if you downloaded them to use. A lot of these first slides are the same, and it's because, like the gamma camera, a lot of the basic principles of radiation detection are very similar. So I'm not going to go over every one of these slides again and make you listen to me lecture on the exact same thing, but I included them because I find it useful as you guys are studying and you're looking at the slides to kind of remember some of the basic same principles of what nuclear medicine detection is and what equipment we use and the basics of some of it. I showed this chart last time. Like I said, we covered gamma camera. Today, we're going to kind of hit the rest of these, which is our dose calibrator, some of our survey meters, GM survey meters, ionization chambers. I don't really cover surgical probe, although it's a gas field detector, and we'll cover the general principles of gas field detector, which the surgical probe works the same. And then we'll talk about the thyroid probe and the well counter, and we'll cover all that today. Just remember kind of in your head that principles of radiation detectors, we're going to talk about, we're still going to reference efficiency and the things that create efficiency. Not so much system resolution, although our energy resolution, our ability to be able to read radioactivity is the same, but we won't talk about so much spatial resolution where we're creating an image, because most of the stuff we talk about today is not creating an image. So just remember, I do want you to remember when it comes to efficiency that geometric, intrinsic efficiency, geometric we're going to talk about today. It's going to be the same. Anything we detect radiation with, our source to distance matters in terms of efficiency and being able to detect what we're trying to detect. And then the other thing that's going to come into play today, of course, is the size and shape and type of detector that we're using. And we're going to talk about different types than we did last time. Also, the geometric, if something is completely surrounding the source of radiation because of that 360-degree travel, if we can surround a source, we can more efficiently measure the entire thing. We'll talk about the well counter because it's the best example of that. Get some of this. Again, it's there to look at. The other thing I do want to mention right here, because we'll kind of come back to this a little more than we did last time, is the idea of temporal resolution. So that's the ability to convert a signal or what we see from radiation into an electronic pulse. And all of the systems still work that way. It's just that we're going to be using a different type of detector to detect that, but we're still changing things into electronic signal. We talked about dead time, which is the process that it takes from when a detector detects something to when we can change it into that electronic signal that we use. And I mentioned non-parallelizable and parallelizable events. Non-parallelizable events, the event happens and it completely goes through the process of creating an electronic signal before it accepts another one. And then parallelizable is where the system is set up to where it sees an event, and if it starts the process and another event comes, it's going to go back to that first event. And so when a system paralyzes, it's something overwhelms the system and it can shut down. And that process of going through the whole entire thing, we call that dead time. And so we'll refer to that again, and we'll get a little more specific. I'm still kind of being a little bit general right now, so just remember that one. All right, so we're going to start with gas field detectors. So when we talk about a gas field detector, this is going to apply to our GM meters, our GM survey meters, our ionization survey meters, and our dose calibrator. Those three things are all gas field detectors, okay? So let me give you, I'm going to start out with kind of basic principles of how these work, and then we'll get a little more specific on some of the other stuff. But they all work over this general principle. So with any gas field detector, you're essentially going to have the unit itself. On some of the gas field detectors that you use for surveys, it might be a kind of a long tube, or it might have a handle with a little puck on the end of it called a cutie pie. Some form of chamber is going to be filled with gas, okay? The gas that is in these chambers is argon gas. And so it's kind of a little bit more dense type of gas. And essentially what happens is inside the chamber, you have a cathode side and you have an anode side. Those of you that have done X-ray, this sounds familiar, right? Your cathode and your anode. And inside the chamber, what happens is when you have magnetic radiation come in and strike the chamber, it will strike the ion gas. What happens when that strike takes place is the gas is separated into an electron and then what we call an ion pair, which is essentially the gas molecule that's been ionized and lost an electron, right? So I'll just call it an ion pair at this point. but you have an electron and an ion pair that gets separated because of that strike. When that separation occurs, because we have a cathode and an anode, the electrons are attracted to the anode and the ion pairs are attracted to the cathode. We apply that, the reason there's that attraction is because there's a voltage applied from positive to negative, okay? So you have a voltage that's applied. So what'll happen is those ion pairs, those electrons get attracted. That attraction creates a current in the system, and that current is what's read out on your meter. Your meter is essentially showing you an amount of current, right? So when you see it, you're looking at MR per hour, or you're looking at some of those things on there, and it basically shows you, 0.2, 0.5, whatever it might be, whatever your meter is. Essentially, what's happening is it's just reading current, and that current again is created by the attraction of the electrons and the ion pair, because there's a voltage applied across that cathode and that anode. Okay, so that is your basic principle of what's happening in there. Now we're going to get a little more specific on how it works and what's happening. But as you can imagine, the more voltage that is pulled across, the more of those ion pairs and electrons are going to be attracted. Like they're going to be attracted at a stronger degree. So that's one thing that's going to vary in the different type of detectors. The other thing is that depending on the strength of the electromagnetic radiation coming in, so a photon comes in, well, what type of photon is it? If it's tech, we know it has 140 keV. It's I-131, we know it's a 364. So because there's different energy levels of that radiation coming in, it's going to ionize a different amount of those argon gas molecules. And so because of that, you'll create more or less pairs of ions and electrons. And the more pairs you have, the greater current that you'll have in the system. Okay, so there's an ability for it to be able to distinguish how much energy it's seeing and because of how many pairs are created. This slide I'm going to skip. It's basically what I just said, kind of written out. But I'm going to go to a little chart that I want to kind of start to explain something called the gas ionization curve. Okay, so this is the gas ionization curve, and what this represents, the x-axis down here represents applied voltage to that circuit. Okay, and then the y-axis represents the number of ions that are collected. What this essentially is showing is the principle that as you increase voltage in your system, you are creating more and more ion pairs and getting a greater response, right? Ions collected. So there's a couple of important places in this curve that we need to recognize, and they make a difference in how different meters are operating, okay? So the first kind of section I want you to look at is what's called this recombination. What's happening here is you'll notice the voltage is fairly low, right? So that means that the pulling those ion pairs and the electrons apart isn't super strong. Usually in this range, what happens is the photon will strike, it'll cause that separation, that ionization, but because the voltage is so low, they'll just kind of recombine. They'll come back together. So it just pops them apart for a minute, comes back together. So there's really not a lot of there's no usefulness that we get out of a meter in this recombination phase, but that's what's happening at the beginning of this curve. Is not enough voltage means there's no separation occurs. Next, we get into the saturation range, okay? So the saturation range is also called the ionization range. It's referred to as both names. What's happening in the saturation range is that when a photon strikes, that separation is happening, and there is enough pull that it's separating those ions and creating a current in the system. In the saturation range, the stronger your nuclide is, the stronger keV, the stronger energy, the more ion pairs it's going to create, and it's going to read those out. So in the saturation range, just remember that you're going to have your ionization chambers. That's where they operate. Ionization chambers operate in the saturation range. In the saturation range, it's where we can get a reading, okay? We can get a reading of how many MR per hour there is, how, sometimes you do an I-131 and you've got to measure a treatment, and you've got to measure your patient before they leave. So you're measuring the radiation coming off your patient. Anything where you get a reading is going to be happening in this saturation or ionization range, okay? As the voltage is increased, you get a greater pull and you start getting more and more pairs attracted. We don't have any instruments that we use that go in this proportional range, but there is a range that for a while it's just stronger and stronger and you get more and more ion pairs. Eventually we make it up to the GM range where the voltage is increased really, really high. At this point, this is the point where the pull is so strong because of that strong voltage that we're going to start getting a couple of other different types of reactions that happen within the gas chamber. So I'm going to go to the next slide. This is where GM survey meters operate, is in this GM range. I'm going to go to the next slide and show you the reaction that happens within the chamber. And then we'll talk about the difference between what makes a GM meter, and then what makes an ionization ionization chamber an ionization chamber, and what we use both of those for. Like, what's the difference? And it has to do with this, with what's happening in each of them. So this is a really good picture for what a chamber really looks like inside more. So I want you to imagine, if you grab your survey meter and you have maybe one of the style that is a tube, this would be like the walls of the tube, both underneath and above here. And then the anode is actually like a wire that goes down the middle of that tube, okay? And this is what a lot of them look like. Not every one of them, but majority of probably the ones that you use at your clinical sites are going to look like this inside, okay? So here's what happens. Remember, we've got our voltage way, way high, so this attraction is very strong. So what's going to happen is as a photon comes in, it's going to have an initial strike with an argon gas molecule. That attraction, as it starts to head towards the anode, is going to be very, very strong. Okay, so you've got the electron that's heading down towards the positive anode. That electron is traveling at such great speed that it actually strikes other argon gas molecules and creates more ion pairs and more electrons. And all of those are then attracted in their respective ways, the electrons down to the anode and the ions to the tube wall or the cathode. And so you get this, what they call a cascade or an avalanche effect, where you're getting multiple hits happening, and all of the gases is really just kind of going crazy in the tube, right? So that's your electrons. Your electrons are traveling to the anode. They're creating all this avalanche or this cascade of firing everything off. Another reaction that's happening at the same time is you've got the ion pairs that then head to the wall. What happens is when the ion pairs strike the wall with the great force again, because your voltage is really high, those hit the wall and they don't kick off an electron, they don't ionize, but what they do is they excite the electrons in the tube wall. So they get very excited. And then when that excitation cools a little bit, it's much like when we talked about solid state detectors last time. It actually gives off UV light, okay? So it gets super excited, calms down, gives off UV light. The UV light actually has the ability also to ionize the argon gas. So you really, cascade or avalanche is a good way to describe it, because you can imagine, top of an avalanche, you got one snowball that starts as something small, and before you know it, the whole mountain is crumbling down. And that's essentially what happens when the voltage is turned up in the GM range, is that this cascade reaction happens. Now, there's one other thing you need to know about this reaction, or one other thing they put in the tube to help here. When that cascade reaction happens, if as you can imagine, because the light is let me go back. The ion pairs are being created, and then there's also light that's creating more, plus all of them are creating it. You're going to imagine that you're going to have the entire system basically overwhelmed, right? It's going to blow all the way to dead time. What they do to kind of reset this, or make it so that the system doesn't just die and is out once you use it, is they add a little bit of another type of gas. And it's usually an organic gas. Methane is the common gas they add. So they do what they call the quenching of the generator. Skip that, not generator, quenching of the system. But they add argon gas. And what the argon gas does is that argon gas doesn't ionize. So instead, it breaks down into smaller molecules and it actually absorbs the ultraviolet light, which eventually kind of slows down the ionization events and lets everything come back to rest. Okay, and it lets everything reset. So
Excuse me.
yeah, go for it.
You mentioned that it was methane gas, and then you said argon.
So argon is the gas that's in there that separates into the pairs, and then methane gas is an organic gas that's called a quenching gas, and it helps fight and break down the UV light. Does that make sense?
Yes, yes.
But yeah, both are in there. Both are in there. The main gas in there that causes the reaction for the initial read is argon. But then they use a gas, methane is usually the one, but organic gas, and it absolves the UV light and kind of stops the process. Okay, so when you get if you're using a GM meter at work and you turn on the clicking noise, right? You turn it on to a sound and you hear beep 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 beep. If you're really using a GM meter, in other words, you're not getting a measurement, you're just getting either an action or not. What will happen is that beep is the process of that nuclide, or excuse me, that photon coming in and having this entire cascade reaction, having dead time, and then resetting. All of that happens in those beeps. So we're talking, when we do this, we're talking like nanoseconds, usually somewhere in the neighborhood of like 30, 40, 50 nanoseconds is what this process takes. So this is happening very quickly. So you don't really notice it on your system. You don't measure something and then you're dead and you have to wait. This is happening very, very, very quickly. If you go and get your meters at work, you can look on the side of them and there's a sticker, and oftentimes that sticker will show you the dead time. They'll print it out and it will say dead time, 40 nanoseconds, 50 whatever the system is. And that's telling you how long it takes to complete that process, okay? So this process right here is the one that I said earlier that's a paralyzable event, right? Because once that first strike happens, it's got to go all the way through the process because of the cascade and be reset because of the methane gas before it can accept another process, okay? And this is what happens in GM meters. Let me go on. Let me go to the next one. So I'm going to kind of divide these two and kind of help you connect at this point. So the two kind of useful, again, we're just talking about gas field detectors, is first the ionization chamber. Remember, that goes in the saturation region, which means we're getting separation, but we're not getting all the avalanche, so we don't have dead time. It's proportional to the amount, either the amount of radiation that is being seen, but also proportional to the energy of that radiation, right? The type that we're using. And so you're going to get proportionality. You're going to get some kind of reading on your meter. The dose calibrator is an ionization chamber, not just survey meter. So both of those things, we'll talk about the dose calibrator more specifically. Some of these are like, you have portable ionization chamber survey meters. I mentioned the cutie pie, which is the one that looks like if you have ones that has a handle and that has like a flat puck on it, it looks like that. And again, if you're doing anything with rate of exposure, that's the same thing. Now, it's very important that understand ionization chambers are low sensitivity, meaning that they can see big amounts of radiation without it overwhelming the system. So what really, when I say high radiation level, it's like the dose ranges that we use, the stuff that you would be around your department. If you spilled a little, if you squirted some out of a syringe, you spilled some and you're detecting it. But anything where you want to get a measurement, certainly. So your dose calibrator, they're low sensitivity, so they can take high radiation levels. Okay. The Geiger-Müller, on the other hand, this is, again, it's in that Geiger-Müller range, which means the voltage is way up, so we get an avalanche effect. We have dead time, and it's just going to be either I'm detecting the radiation or I'm not. It's going to be an on or off. If you are looking at your meter and you have something that's being measured, you're not in the Geiger-Müller range. You're using ionization. Geiger-Müller would be it's very sensitive. So this is low level activity. So if you're using really using a Geiger-Müller, it's because you're trying to find, you're getting a reading from somewhere and you're trying to find a little area that has tiny bit of radiation and detect it. Very sensitive. Again, no proportionality. It's either fires or it doesn't fire, but very high sensitivity because that voltage is way, way up. Okay. A lot of times if you take your meter, you'll have the box portion, then you have the wire that's connected to a head. you should, when you go back to your work, ask one of your techs. You can actually remove the wire and the meter, and most of those boxes have a tiny little chamber in them that's a GM chamber. So if you take on your on the box, you can turn it, right, and you can change the voltage, you can change the different things on it. One of them on a lot of the meters says GM range. It will tell you that it's changing the voltage to the GM range. And then inside, you don't see it unless you open up the unit, but there's a tiny little tube inside, and that's the Geiger-Müller counter, and it's really, really sensitive. Again, very low level activity that we're trying to look for, and that's the difference. Now, I will add this on there too. This is just talking about gas field detectors. The other thing that you will see at work, or at clinicals, I should say, is there is actually meters that are essentially the same as your camera. So there are meters, and they're shaped very similar to the other ones, a long tube. And basically what you have is you have a photomultiplier tube with a crystal on top, and that's literally what you're using to detect, right? So what I would suggest, and you'll do this as part of our quality assurance class in summer, but I would do it just in advance to kind of look at things, is I want you to go look at the meters you have at work, and find out what they are. Like, take a look at them, see which ones are ionization, see which ones are GM. Again, some of them have an ionization head and a GM head, and it just depends on how much you turn those knobs. When you change those knobs, you're changing the voltage in the system. So go look at them. Also look at the sticker on the side. See if you can find out where it says the dead time. The other thing you can do, if you know, I know you guys are like have nothing to do and you're not busy at all, but the other thing you can do is you can actually look up, all of the meters will have the manufacturer and they'll have a number on them. You can actually look them up on the internet, and you can find manuals and things, and it will show you all of this information. It will tell you what kind of chamber you have, what you're using, what the voltage limits are on it, what the dead time is, and you can see exactly how it's constructed. But again, when it comes to gas filled chambers, these are the two things. What I want you to remember, big points I want you to remember is, again, saturation region or ionization, whichever you call it. It's proportional, no dead time, things like dose calibrator, and we can get a rate, we can get a reading. Geiger-Müller, high voltage. Oh, and this is low sensitivity, high radiation levels. Here we're very sensitive, so we're looking for low exposure, low little things. There's no proportionality. It's either going to give you the click, and that's telling you something's there and going through the whole process, or not. Okay?
So I have a quick question.
Absolutely. Thanks for interrupting me.
The Geiger-Müller, it beeps, right? It does the beeps.
Yes.
But it also has the gauge on it that shows what the level is. Is that the same thing or not the same thing?
I'm going to say yes, and then let me explain some more. And it gets super confusing because I'm betting that a lot of the ones you're reading are actually crystals and not gas filled chambers. But some of them are set up to make a beep even when they're giving you a reading. So it depends on your meter. But a lot of them you'll turn it to something that says GM right on it. And that's where you know you've got the voltage turned all the way up. Again, some of those meters will still give you a reaction, even if it's a GM. It'll give you an on-off reaction, so it'll bop up and be done, right? So that's GM, and it's just giving you that instead of the beep. Most of them you can turn the beep on or off. But if it comes up and it's sitting at a reading and it's bouncing, it means that you're somewhere in a neighborhood where voltage isn't high enough that you're getting the avalanche. You're not getting it on and off. If it's sitting in a range and it's staying there, that's what it's doing. But again, that's why I want you to look, because it's likely that you might not be using an actual gas field detector. You might be using a crystal. And in the case of a crystal, it works exactly like your camera. And the crystal can see multiple events and give you a reading, right? Because it can look at how much radiation is coming and measure it. And that works in exactly the same way as your camera does. So did I help answer that question, or did I just confuse you more?
Yes.
Okay.
But I have a question. So, like,
Yeah.
using the Geiger counter that we have, it's like it has like is it more of an if it's crystals, is it like an uptake thing? Because whenever we're using it, it goes and it starts, and the longer you hold it there, the better the reading is.
It's probably, does it have a head, or is it just the box that has like a window at the bottom?
It has the puck like you're talking about.
It does have the puck. It's probably it's probably an ionization chamber. If it was Geiger-Müller and it was peaking out, you would just get the dead time. What I'm going to guess, if it's usually those pucks are an ionization chamber, and so again, it can give you a reading. And yeah, the longer you stay there, it's going to keep adjusting that reading and seeing how much is there. Are you using that when you let patients go, or are you doing survey meters with it?
Well, we actually used it yesterday to send back a, a flood sheet to the manufacturer because we got a new flood sheet in, and I helped them package it up and everything.
Okay, cool, awesome. That's a good opportunity. Yeah, so it's going to be, if I had to throw a guess out there, especially since it's the handle with the puck, the cutie pie type, that should have been an ionization chamber that you were using. And again, like you noticed, you kind of held it there, getting a reading. And again, remember it's low sensitivity, so it's going to sit there and count and kind of figure out where you're at, but it's high radiation. If you were using a GM meter, it just would have peaked out, and you would have been done and not been able to get a rate out of it. Most of the time, it's hard when I've noticed students in path, and even when I learned this, it's hard to understand because we use the terminology interchangeably, and they're really not. We say Geiger counter, and we mean it for everything, but a Geiger-Müller meter is the type that again has the avalanche. We should be saying ionization chambers if we use another way, if it's a gas field detector, and then if we're using a crystal, people call that a Geiger counter, but again, we're confusing it with Geiger-Müller, so it can get somewhat confusing. On your
We also use this one for checking our doses when they come in the bag, 3 meters against
so
it.
That's why I said anything that you're measuring and you're getting a rate, you either have an ionization chamber or you have a crystal. If you're just trying to take something and sense low levels of radiation, just listening for a noise and not getting a measurement, then you're using a Geiger-Müller tube. And that's why I say you probably don't use a Geiger-Müller tube hardly ever. It's also why I told you about look into your meter, because a true Geiger meter, often you can take the wire and the end off. And if you open them up, you can actually look inside, and there's the tube, and it's actually tiny. It looks like a little vial almost, but it's like silver in color. And that's your actual Geiger-Müller chamber in there that fires off every time. So go do some research, but in terms of general principle, these are the two types of, it's going to ask you about these on gas field detectors in tests. And again, just always think ionization chamber because it's in the ionization range if you're getting a rate. And if you're talking about a Geiger-Müller counter, it's never going to be anything with a rate. It's just detecting very small, like you had a spill and you've got to clear an area of a spill or something like that, but you're not worried about getting rate. So you'll turn it way up.
Awesome, thank you.
Yeah, good question. Thanks for interrupting me. Okay. Let's talk about our survey meters in terms of quality control. So both the GM and the ionization survey meters are identical in terms of the quality control that needs to be done. They have to be calibrated annually. That is typically going to be done by a physicist. There's usually companies that you'll send them to. There are some places that have a physicist come in and check on them. But typically that calibration will be done by a physicist and many times sent away. That has to be done annually, or after any type of repair, they have to recalibrate the system. Not much more you need to know about annual calibration than that. You won't ever be doing anything about it, but just remember that they have to be calibrated annually. The calibration date has to be on the instrument. And so that's why I also want you to look at that sticker on the side. There's usually a sticker on the side. It's going to have a calibration date on when that instrument was calibrated. So if you're in a department and you find yourself after you've gotten through school and you end up being in a small department where there's one tech, these are the kind of things you got to pay attention to when you're looking at your survey meters, when you're doing quality control. Like pay attention to that date because you're going to be responsible to make sure that the calibration gets done. Battery needs to be checked every day. Most of your survey meters will have a button on them. You push the button and then it will give you a reading on your meter that is checking the battery to see if there's enough power. Obviously, it's pretty important to check your battery because if you're out of battery, your survey meters aren't going to work, and you might be walking around detecting and thinking you've got nothing, but it's just your battery's dead. So those have to be checked daily. each meter is going to come with its own check source. Usually it's a cesium 137. Sometimes they're cobalt, and they're a tiny little disc or puck shaped. Usually they're less than 10 mics, so it's not a lot of radiation, but they'll usually be stuck right to the side of the meter. I have worked in one place where it wasn't stuck with the meter; it was in a drawer, and it was written down with, you know, which meter it went with. So you may see that as well. A lot of the times they'll put them right on the meter themselves. Very, very low, so they usually don't affect your meters too much, but you use those for the cals that you do every day. Daily reading should be taken before you use them daily and compared with the calibration. So the sticker is also going to have written down what the measurement should be on your 10 mic source that you have on the side. Okay. Now, most of you, if you've done QC in the morning, which I'm sure you all have by now, you probably don't realize that that sticker has that on the side, because you usually have a system where you put all this information in on the computer, right? And so you go in the morning, you take all these measurements and write them down, and then you go on a computer and you enter them all in, and the computer tells you whether you passed or not. All that's happening is that computer, some tech at your department, has gone and taken that sticker and put that information in the computer, so that when you put, you know, let's say you had a background reading of 0.02 or on your meter or whatever it might be, that it knows that that's accurate based on that sticker. And that's all done when the calibration is done. Okay. That measurement that you do has to be within 20%. Okay. So good things on this page to remember is annually calibrated or after repair. Calibration date has to be on there. We have to measure the battery daily. We have to measure the small source daily, and then it has to be within 20%. Okay, so that's for both GM and ionization survey meters. It also applies to anything you have that may also work on a scintillation base or a crystal base. Okay, we're going to move on to dose calibrator. There's a picture of it. It's probably similar or something similar to what yours looks like. This is actually an older one. A lot of the newer ones kind of have more of a digital display and do a lot of automatic measurements, but this is kind of what a dose calibrator looks like. Again, this is what we're going to use to measure your dose, you know, before you do patients every day. Let's see what I want to mention here. Yeah, so you guys have used these. You obviously know it's used to assess the amount of radioactivity in your dose prior to administration. Please make sure you're measuring your doses. I have seen a couple of places that I worked where there were techs that weren't measuring the doses. They were just taking them out and injecting patients, and you always want to measure. It's required by law. The dose calibrator operates in ionization or saturation region. Again, why do we know that? Because we're going to get a measurement of some kind. When we put our dose in, we're getting a measurement in millicuries or becquerels, right? So same thing as a anode and a cathode, and functions because of the current that's created by those separations. Again, if there's more activity in there, it's going to give more current because there's more separation of the ions and the electrons. The dose calibrator has electronics that convert the voltage that it sees, or excuse me, the current that it sees to voltage, and then applies a calibration factor for each radionuclide that you use. So what do I mean by that? So when you go in there and you put a dose in, there's usually a button that you've got to tell it what you're measuring, right? So I'm measuring tech, or I'm measuring I-131 or rubidium, or whatever you're measuring. You've got to do that because, again, all a dose calibrator sees is it sees current, right? It doesn't know what you're putting in there. It's just going to say I have this much current. So if you didn't correct for the fact that it's tech or it's I-131, the dose calibrator each time would just have a certain current that it would read out. So what's happened in advance is that when your dose calibrator was set up, it was set up to read the different types, several different channels that apply a factor that corrects for and reads the current based on whatever you're looking at. So that's why it's important that you put a dose in, make sure you're measuring the right thing, that you're measuring tech instead of I-131 or whatever it might be, because it's going to read wrong if you don't have the right factor applied. This is what I was I was mentioning here, it's actually part of the National Regulatory Commission rules that we have to follow, and that your license here at your workplace is based on. That any radioactivity administered to a patient or a research subject has to be at-state in the dose calibrator. Okay, I'm sure that will be a question on boards. It would shock me if it wasn't. Okay, so dose calibrator QC. The NRC requires that the instrument has to be calibrated in accordance with nationally recognized standards. Two organizations that kind of oversee not just dose calibrator standards, but also for your meters, are American National Standards Institute and American Association of Physicists in Medicine. These two institutes are the ones that actually will give you your sources as well that go with the dose calibrators. And those sources are measured and pre-calibrated so that they know exactly how much they should be. And then obviously that's why you kind of use them as a standard. Your equipment has to match and be able to read, you know, the thing that says it is, right? Whatever the reading of it is. So we're going to go through dose calibrator QC. This one's a little bit more involved. Most of these you don't actually do. You do constancy on a daily basis, and hopefully you've had a chance to do that. That's what we were kind of just referencing. But the four that you need to know for boards are accuracy, constancy, linearity, and geometry. So I'm going to go through and kind of try to explain each one of those. I've written a bunch of bullet points here. But the first one is accuracy. It uses two calibrated sources, again, traced to the NIST, and those are measured. And then what happens is you're going to assay with your dose calibrator those sources, and you've probably have cesium and cobalt. There's sometimes some other smaller sources, depends on what your facility is doing and the way your equipment's set up, but you'll have sources that are calibrated and should be a certain activity. Anything greater than 10%, actually I put less, didn't I? Less than 10%. Anything greater than 10% triggers a repair action. Accuracy is done annually, and accuracy is usually done again when your camera's set up, or done annually, and usually you'll have a physicist that comes in and does it. It's unlikely that you'll be doing accuracy, but just remember the accuracy is super simple. It's just the standard measurement doses. Does your equipment read them exactly with what they say they should be in terms of activity? So, and then just remember 10%. 10% is kind of a good number to remember pretty much on all of these. 10% triggers repair action or triggers a problem. The next one is constancy. For this one, this is the one that you use to verify that you're measuring accurately and you're measuring precisely. So again, you're going to usually have the two long-lived isotopes, the cobalt and the cesium-137. This is going to be measured daily, and it's going to be measured on every one of the nuclide channels that you use, right? And so this is the one you've probably done, and you've written down the numbers and then gone and put them in your computer. Again, all of that stuff that's in the computer is based on when someone did the accuracy test and when they set up your dose calibrator. Okay, that's performed daily, and essentially just making sure that your machine doesn't vary over time. That's why they're long-lived isotopes. We're going to measure them every day, make sure each channel is functioning right and reading within the range that it should. Again, 10% trigger on that one as well. I did not write that down for some reason, but just remember 10% pretty much applies across the board on the ones where you do measurements. So 10% measurement. The next one is linearity. And basically linearity, what linearity does is it makes sure that your dose calibrator can measure a dose anywhere from a very high dose to a very low dose. And that across that range of activity, that it's accurate at each measurement of the range, whether you have a very high dose or whether you have a very low dose. It's sensitive to all of it. It's linear across that whole space. Okay, so essentially what they do here is they take a radioactive a source, some sort of dose, and usually you're not doing this. Usually, again, this is a physicist. So they're coming and they'll measure that dose in the morning, and then they'll measure it 3 to 4 times throughout the day, and then they'll document it. And they usually have software that they'll plug it into the software, and it creates a logarithmic graph that should take into account decay over time, right? So the same dose, it's going to decay over time. And essentially what the software is doing is it's comparing it to the radioactive decay equation. So it's really doing what you guys have been doing with the math, right? Is it takes it and it says, okay, I've measured it here, 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 and here throughout the day. According to the math, it should measure this much at this time, and this much at this time, and this much at this time. Does it? Does your dose calibrator do the math correctly? And is it able to measure? Is that measurement lying where it should measure? And that's what the linearity is. It's performed quarterly. One other way that linearity is done so that a physicist doesn't have to spend all day at your place is they bring in, it's a set of tubes that they put down inside the dose calibrator. And it looks kind of like, I would compare it to I think those Russian nesting dolls, if you know what I'm talking about, where it's like the doll within the doll within the doll, right? So there's tubes.
We had to do that.
What's that?
We did that last month.
Oh, you did? Okay, cool, perfect. So you've done it. I've never had to do it. We've always had a physicist that did it. But yeah, so you basically have tubes within tubes. And so what you can do is you can mimic decay over time by using the tubes. So you'll put the radiation source in with the smallest tube, and then you'll continue to put larger tubes on, and that's going to increase the attenuation, which represents a decay. And again, with each one of those tubes, the physicist should know what the measurement should be and how much it should bring it down in activity. And again, they're going to make sure that matches within 10% again. Okay, so it's basically just measuring radioactivity over time and that it's decaying, and then measuring that decay accurately and correctly. Okay, the last one you need to know about is geometry. So geometry basically just takes into account the size and the shape of the container that your doses are in most often. Okay, so when your dose calibrator is set up, they will do geometry, and what they'll do is they'll take the common syringes you use. So likely that's going to be like maybe a 3 millicurie syringe. No, not 3 millicurie, 3 ml, 3 milliliter syringe, and a 5 milliliter syringe. Okay, and what they'll do is they'll put about 2 millicuries in the syringe in a very small amount of volume. Then they'll measure it. Then they'll fill it up slowly over intervals until you're about 67% full. And what they're looking to do is to see that you get the same measurement regardless of the volume size changing. The reason that this is the case is because, again, they want to make sure that the ability of that machine, because you set it down inside, has an ability to look at all of the space is measuring correctly, that you're not getting anything weird with the argon gas reactions. Everything's symmetrically able to measure that no matter where the radiation lies within the chamber. Okay, and so that's why they do it that way. They slowly increase the volume over size while keeping the radioactivity the same. This is performed when your dose calibrator is set up, or it's performed anytime where you might be using a different container for your radioactive sources, anytime it's changed in any significant way. Before I was working in cardiology and I was in general nukes, we did treatments for a liver called TheraSphere. Maybe where you guys are at, you see TheraSpheres sometimes. When we first started doing TheraSpheres, we had to do our geometry because instead of a syringe, they came in kind of a short, stubby, kind of wide vial. And so they felt like that was enough of a difference that they did geometry so that it could measure accurately. Then later they ended up doing a whole different thing. But anyway, anytime it changes significantly, then geometry will need to be performed again. All right. I liked this chart and I threw it on because I can almost guarantee these are boards type questions. They're going to want to know how often is accuracy performed annually? When is constantly performed daily? Linearity is quarterly, and then geometry again is when there's a change in configuration or when you first set up. So I really liked this chart. I don't think you need to have these sources memorized, so that's why I didn't highlight that side of the chart. But definitely this is something that I could easily almost guarantee would be on boards. The other thing is to remember that 10% trigger limit when you're doing quality control. All right, so now we're going to talk about well counters. So everything we just did is the gas-filled stuff, Okay, so that's all the gas field stuff. Again, I mentioned there might be some surgical probes and a few little things. There's surgical probes that are tiny little gas filled chambers that they use to detect things during surgery. They're still going to function in that same way. And again, if you're getting a rate, you've got an ionization chamber. If you're just detecting, then you're probably up in the GM range. Okay, so I'll kind of leave that for the gas filled. Well counter is not gas filled. It's done by scintillation. So what you're looking at here is this is it's basically what we learned last time with the gamma counter. Okay, you literally inside your well counter is a photomultiplier tube with a crystal on the front of it and a preamplifier in the back. So it literally looks exactly the same. That whole setup is just surrounded by a shield, right? It's just surrounded by usually lead or tungsten is what they are. That's why they're so heavy. But that's all surrounded by a shield. Now, what's unique here about a well counter is what they've done, and this is different than your camera, is there's actually a hole bored into the crystal. Now, remember when we talked about sensitivity, right, and efficiency of something that measures, what we said is because that radiation travels in 360, the most sensitivity was of the radiation coming off, what are we able to gather and measure? So the most sensitive thing you could ever have is if your detector could completely surround the radiation source, right? Well, well counter is the closest you get to that. And this is why, is because it's completely surrounded except for one side. Everything is getting measured here except for whatever photons are kind of coming straight out the top of this thing, okay? So because of that, well counters are super sensitive. This is why they're used for wipes. Again, when you think well counter, again, we're not looking for necessarily, we're not measuring a dose or anything like that, right? Well counters are there to try to detect small amounts of radiation, okay? So you do your wipes. This is what you do your wipes with, or if any of you have done, sometimes with sinus leaks, you'll do what are called pledgets, where they put the pledgets up in the nose in surgery, and you give them a radioactive dose and see if there's a leak, CHF leak, and it gets on the pledgets, and then they end up measuring each of those pledgets in the well counter. Again, they're looking for tiny bits of radiation. And as you can imagine, that efficiency means that it has a limit to it. So because it's so efficient, it gathers so well, it limits the maximum amount of activity to about 1 microcurie, okay? When it gets beyond 1 microcurie, because of the efficiency of this system, it kind of peaks out the system and you get a lot of dead time because the crystal's just constantly firing and the electronic doesn't keep up very well. It overwhelms it. You would probably, if you put more than that in, you'd get a reading, but you couldn't guarantee it was accurate because in reality, you probably have way more radiation coming off, but the system is measuring it as something lower because it's trying to keep up with the amount of efficiency that's created with this. Because again, also remember in your camera, not only are you measuring the crystal or getting radiation from one direction coming in, but you've also got your bores and your holes, and you're trying to cut out all of the stuff that's going at weird angles, right? And so I mentioned before, you're getting a tiny percent. It's like 1 or 2% efficiency with a gamma camera, whereas this, I don't know the percentage, but it's extremely high. We're not trying to block anything. We're trying to detect small amounts. So again, on this one, I want you to remember again that this is done with crystal. It's a scintillation system, and I want you to remember it's such a high efficiency that we can only do about 1 microcurie. Beyond that, you're not going to get an accurate measurement. But really, if you're going beyond 1 mic, you might be measuring something, it'd be more of a situation of dose calibrator. We're just using this for wipes. We're trying to find teeny amounts of radiation on things with a well counter. Okay, the next one we'll talk about is the thyroid probe. This is what a lot of them look like. And most of the thyroid probes I've seen look something like this, but let's talk about kind of how a thyroid probe works and what it's doing. Again, thyroid probe is scintillation based. So you have your crystal on the front of a photomultiplier tube with a preamp in the back. That electronic signal that's created exactly like your camera then goes to a computer. In this case, the computer, we're not creating a picture, we're creating counts, right? Because we want to measure thyroid for treatment and determine how much of our iodine has gone to the thyroid. And so, and again, you'll learn more about that in other classes and specifics, but essentially we're measuring counts. Now I wrote on here to try to kind of make a distinction. Why if we've got a body part in front of something that scintillates, why don't we use this to image? Why don't we image the thyroid? And the answer, and again, you notice on here, it actually has collimators. That tube that comes out at the end of your thyroid probe are considered collimators. But the reason is that we don't have a way of, we have a very wide open collimator, and we don't have any way of keeping things parallel. So this is going to accept counts at all angles coming in, because again, we're just trying to measure the activity in the thyroid. Okay, so I wrote this down here. I could see that being a test question. That what do we call it? What type of bore is a thyroid probe? It's a single bore collimator. So if someone asks, do thyroid probes have collimators? The answer is yes, and they're single bore. One hole accepts everything really big. Okay, so if we put a collimator on the front of this, you could conceivably find a way, that had many bores and holes that were in the millimeter range. You could conceivably find a way to get some type of image off this, but again, single, really wide open bore hole that we're just trying to get counts from. Okay, so that's thyroid probe. All right, I'm going to give us a 5-minute break. That's covers all of the kind of rest of the equipment that we're going to talk about today. So let's take a 5-minute break, and then when we come back, we're going to do a brief, I hope to keep it brief, discussion about statistics and why we care about statistics in nuclear medicine, and then we'll be done for today. So let's see, what's my watch say it is for 6. So let's come back at I'll start around 5:01, something like that. Okay.
Cool.
All right, I'm back. Let's go ahead and get started. Okay. So we're gonna have a discussion about statistics. Before we do, I wanted to bring up this slide again. You've seen it a couple times. The reason I bring it up again is to remember that we're going to talk about a lot about counts when we talk about nuclear medicine and statistics. And just to remind that essentially when we talk about a count, we're talking about a strike of the photon, on the camera or whatever you're using to measure radiation. We're talking about counts, right? And counts create our image. And I wanted you to remember that in the end, we're not talking about a photon. A photon is not an actual thing, but it's a very, very tight packet of energy. And then we call that a count. And so that's what we're referring to when we get into this. Okay. So there's a couple of principles I want to start with. You might be wondering, why do we need to talk about statistics in nuke med? Like, why do we even care? So what I want to do is I'm going to share some statistical principles. And what that's going to do is it's going to allow us to have a discussion, and you're going to have to kind of trust me as we talk about statistics here. And we'll go to a point where it'll give kind of a payoff and teach us about something really important in nuclear medicine and why we do what we do. Okay. So you have to just kind of trust me over this first part, and I'll try not to bore you out of your mind. So I want to talk about two principles. One is precision and one is accuracy. Okay. When we talk about the precision, what we're talking about is the spread or range of some data point. In our case, we'll be talking about counts. So the spread or range of something, the greater a range of data you have about something, the less predictable and reproducible it is. Okay. So when we talk about small precision, we're talking about a small range of something. If something all lands within a certain small range of data, we can predict that it will do it again. Okay. Accuracy, what accuracy means is instead of talking about a range or a spread of data, we're talking about what is the true or gold standard that we're looking for. Okay. What are we aiming for? What is the accurate thing? Let me tell you, to kind of make, those are very kind of convoluted ideas. So let me give you something a little more specific that's real world. Okay. So I have a 9mm handgun. I'll sometimes take it out to the range to practice shooting. Okay. So when I go to the range, I get there, get all checked in and everything. When I'm aiming at the target, I aim for the bullseye, right? And typically what I end up with is a spread of bullet holes on my target that are up and slightly to the right. Okay. So I'm up and slightly to the right of what I'm trying to hit. However, my spread of bullet holes is actually a pretty tight range. Okay. So they're pretty close together. So let me ask you guys a question. When I shoot my firearm, am I precise and accurate? What do you think?
Yes.
Yes to which? Both?
If you're good, yes.
So, like I said, when I do it, I'm usually up and to the right, but I'm in a very small spread.
You're precise and accurate.
but not precise.
Okay, all right. Who else? Was that Raymond? Did you come in second?
Yeah,
Okay, what did you say? Say that again.
accurate but not precise.
And why do you think that?
Because precise would be a bullseye. Accurate is just if your bullets are all together.
Okay. Does everybody agree with Raymond?
No, because if you hit there every time, you are precise and you are accurate, because if that's where you know you're going to hit, that's where you're going to hit.
Okay. So anybody else? You guys are thinking correctly. Go ahead.
You're precise, but your scope isn't accurate, and not like if you're hitting in the same spot always up and to the right, maybe your scope's not dialed in.
Okay. Yeah. So you guys are hitting it. So again, remember that precision or being precise is determined by the range or spread of data points. So in this case, we're talking about bullet holes, right? So I have a tight grouping, which means my precision is tight. So I'm precise, but I'm not accurate because what am I trying to do? I'm trying to hit the bullseye and I'm not hitting it, right? And what this does is it makes me somewhat predictable, okay? Because if you go to the range to me and be like, oh, I've been here with Mike, I've seen him shoot before. He's gonna shoot, you know, his next time he shoots, I can predict it's gonna be up and to the right. Why? Because I do that a lot. I go up and to the right, and you're gonna be able to look at that. So I am precise, but I'm not very accurate. So keep that in mind as we start talking then about data in terms of counts, and we're going to mention some more statistical principles, okay? Good job, you guys. So I'm going to give you quick reasons why we use statistics in nuclear medicine. There's 4 kind of main reasons. One is that radioactivity is a random process. What do I mean by that? Well, we talked about meters a minute ago. When you get out the meter and you're going to measure something and you have the sound on, what do you hear? You hear beep, 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 right? So you're getting it random. Now that might seem counterintuitive to the fact that we've talked about radioactive decay, and we've talked about things like when we do our math equation, we've talked about Euler's constant. So radiation is constant over time. That's why we can measure it and know what its level is going to be over a 6-hour period, a 10-hour period if I need to dose my patient here and there. But radioactivity is still random. It's still a random process within that reliable decay, right? It's still happening at random, and you can hear that when you do it on your meter, okay? So statistics is all about the random nature of things. We can't say something will happen for sure at this time. We have to look at statistics. So radioactivity is a random process. Statistics are also going to affect diagnostic accuracy, and we'll talk about what that means and why we're reliant upon statistics to know that we're accurate in our diagnosis. The radiologist is very reliant upon statistics. And then statistics can affect our image quality. Again, how many counts are we getting and what does that mean for our accuracy and our reliability? And then statistics are also a measure of machine accuracy. Can you guarantee our machines are accurate? We use statistics to do that, okay? So let's talk about 3 quick little statistical principles. First one's mean. You're probably familiar with mean. You probably started learning about mean in like junior high math or whatever, right? So the mean is you take a group of data points, in this case a group of measurements, and you basically say what are they, and you're going to add all those up together and then divide it by the number of measurements or the number of data points, and that gives you the mean, okay? So it's kind of the average, okay? Standard deviation is a measure of the deviation or spread of the data points from the mean, okay? So if the mean is the average, how much does my data spread from that average? If I had a standard deviation that was very, very narrow, that means that my data is really close to that average. But if I start getting a wide spread, it means I've got data points that are kind of far off from the average, okay? So that's your standard deviation. This is a measure of precision. Again, I mentioned precision is our spread of data, right? So this is a measurement of my bullet holes, and where are they? Are they tight grouping? Or are they a far apart grouping? Okay, that's what standard deviation helps us with. And then there's something called coefficient of variance, or the other way that this is talked about is percent standard error. Okay, and this is essentially just the error that's expected within statistical data. In our case, because and in statistics, we're talking about random things, not things we can nail down. And so in this case, due to the random nature of radioactive decay, we are going to inherently have some percentage of error in the data that we collect. Okay. All right. let's talk about real world again. So I'm 46. Okay. And at 46, I can get like an okay insurance policy, like life insurance policy, right? But when I'm 65 or 70, I can't get as good as one as I could get now. And when I was 20, I could get a really good one. I can't get that good one now. Why? What do you guys think?
Because the odds of having to pay out a policy are higher because you're older.
Yeah, they know, right? They know that the likelihood of what happens, I'm going to pay over time. If I'm 20, the likelihood that I'm losing my life anytime soon is pretty low, right? And so they're like, hey, we can sign this guy on at 20, give him a decent deal, but by the time he pays us payments for the rest of his life, he'll probably have paid more money than we pay out in life insurance. Not always the case, but you know, it's a good deal for them. Whereas somebody that's older and probably has some health conditions and they're going to die within the next 10 years, you know, you're not going to get a good policy. Why? Because it's all about risk mitigation for them and making money, right? And they need to make their money. So let me ask you this question. How do they know that? How do they know that?
Because everybody dies.
Everybody does die. That is true. But how do they know that if I give you one at 20, you're not likely to die? Let me ask it this way. Let me ask you just maybe a different question that will get your mind going. Do insurance companies deal with 5 clients? Or do they deal with thousands, hundreds of thousands? And what difference does that make?
They have statistics that show that younger folks live usually to make it to the older folks.
Yeah. So if you have thousands of people that you're working with over time, you can start gathering data about thousands of people, right? And that the reality is that the more data you have to look at, what will start happening is you'll start seeing predictable patterns within the data, right? So that's why life insurance can operate the way it does, is because they know over time, yeah, I'm 20, I might get in a car accident, but the predictable data, if you look at thousands and thousands of people, is that the data shows that's not going to happen. However, if I'm 80 years old, the data showing that I'm likely to have a stroke or a heart condition is much higher, right? So they're not going to insure that. So the more data that you're gathering, the greater chance that you're going to have to be more accurate. Another quick example, if I had 5 pennies and you and I, we tossed them on the table, you can imagine that sometimes you're going to get a multiple combinations, but the likelihood is you're probably going to get like 3 heads, 2 tails, or 2 heads, 3 tails most of the time, right? It's kind of the average in the middle. It's probably not going to be very likely that you do all heads, and it's probably not going to be very likely that you do all tails. Well, if we did this 100,000 times, we're not going to, but if we did, we would start to see, again, patterns within that data. And when you map out patterns in data, you have what's called a Gaussian bell curve. You've probably seen these in other classes and other studies, right? That's essentially what a bell curve is it says in a bell curve, you have the average right up the middle of your data. And then what you have is, as the curve goes out, essentially you have all of your data points. So if on our penny example, probably in the center here is like 2 heads, 3 tails, right, on one of these 2 sides. And as you go out towards the edge, clear out here is probably where you have all heads, and clear out here is where you have all tails. They're just much less likely, okay? Well, this is where you start to look at what's called a standard deviation. So, and a standard deviation helps us to look at probability, okay? So when we say 1 standard deviation, that means we're going to look at 68% of the data. Any data set that you have, 1 standard deviation is what we cover as 68% of the data, right? So we're limiting our data, and what this says is that 68% of the time, if I say, okay, I'm going to guess that the next penny roll is going to be 3 heads, 2 tails, we're probably going to be right about 68% of the time. So this tells your predictability, right? You have more predictability. Now, what I want you to notice is that if you allow more combinations to be right, so say this is 3 heads, 2 tails, but then we're going to say 4 heads, 1 tail, you're going to be right 95% of the time. So the more data you let in, the more you're going to be accurate, right? You're going to be more accurate, but we're going to see that it's less likely that you'll be able to guess it, even though you have more data, depending on what you have. So just remember that 1 standard deviation is going to be 68%. We could guess it right. As we let more data in, we're going to get more correct over time. Okay. So let's look at how to calculate standard deviation, and now let's talk about what we do in nuclear medicine. So in nuclear medicine, we're talking about counts. Okay, we're not talking about penny flips or any insurance or anything else. We're talking about counts. When you put someone under the camera, you're getting a certain amount of counts. So to measure standard deviation and to get our spread of range in nuclear medicine, what the equation is actually pretty simple. In other statistical data, when you're looking at more than just single counts, it gets a little more convoluted. But in this case, to figure it out, it's just plus or minus the square root of the number of counts you have. So to get a super basic understanding here, if I had 100 counts and I took that and I hit the square root button on your calculator, so the square root of 100 is plus or minus 10. What that would mean is that the range you would be allowing in one standard deviation would be anywhere from 90 counts to 110 counts, okay? So I would know that I'm accurate within that range to one standard deviation. Two standard deviations, it's going to allow a greater amount of data in, right? 80 to 120, because you would just do 2 times the square root of 100, which would be 20. Plus or minus 20 from 100 is 80 is minus 20, and 120 is 100 plus the 20, right? So again, you have a bigger range of counts, okay? So it's 1 standard deviation, 2 standard deviations. When a radiologist reads a scan and they make a report, on that report, it's going to say this was read to 2 standard deviations is usually the standard, right? And so what that means is because 2 standard deviations is about 95%, then they're going to say my confidence level in this is 95% accurate, okay? And that's not an opinion they have of themselves. That's actually going to be based on the data, which is I'm going to connect and show you here in a minute, okay? So when we read the 2 standard deviations, it's 95% confident range. Now, let's talk about error. Because what happens, unfortunately, is when you increase your range or your spread of data, you could become more accurate in predicting what it might be next, but the percentage of error, it goes bigger when we spread our data, okay? So coefficient of variance or standard error is the error to which is expected due to randomness of radioactive decay. The way you figure percent error is you do the square root of the counts divided by the counts times 100, okay? So in this case, if we did 100 counts, okay, so the square root of 100 is 10. So we did 10 divided by the number of counts, which was 100, 10 divided by 100, and then we multiplied that by 100, and we get 10%, okay? So if you have 100 counts, you let 100 counts hit your detector, and we say, what's 1 standard deviation? So we know we're about 68% accurate. We'd have a 10% error in there, okay? So there's likely we're getting good data and it's accurate with what we see on our screen. However, there's a 10% likely that there's errors in the accuracy of that data or that image or that counting, thyroid, whatever it might be, okay? So at 100 counts that we allowed, 1 standard deviation gives us 10% error. If we did 2 standard deviations, again, 100 counts, 2 standard deviations mean we're 95% confident in our prediction, but we've gone up to a 20% error, okay? Let me show you one more example here, and we'll get bigger counts so you can see, because this is where you start to see why counts in nuclear medicine are important, okay? So we have our 100 counts, and we're going to do 2 standard deviations since that's what a radiologist reads at. So we got 100 counts. If we figure that out, our standard deviation would be plus or minus 20. So we have a range from 80 to 120 that we can predict within, and we have a 20% error. Now, watch this. If we go just from 100 up to 10,000 counts, so we're allowing more counts, our standard deviation, when we figured it out, would actually be plus or minus 200, okay? So there's a bigger range, and that means that our 10,000 would go from 9,800 to 10,200, because again, that 200 range. So a big range of data, but look at what happens. Look at what happens to our error. The error goes way down, okay? Greater count amounts, way smaller error, all right? So as the number of counts increases, the variation increases, but the percent error goes down. And we care about the percent error, because remember, I just told you a cardiologist will read something to 2%. Now let me give you kind of let's talk about this in a situation that you've been in, right? So you're at clinicals and you're going to do a bone scan, right? You put the patient, let's just say you're doing a static of the knees, okay? So you're doing static of the knees. Likely at your facility, they're gonna measure that for, you guys tell me what you do, maybe 3-5 minutes? Do you do it at a certain amount of counts? What are you doing with your bone scans when you do a static knee?
So far ours, I think we're at both. We have a certain number of counts and a minute amount.
Okay, so great. That's actually an awesome way to do it. So let's just say for purposes, now you guys have sat there and watched this on the screen come on, right? As your counts come in and it starts forming the image. So let's just say for argument purposes, let's say you do a static of the knees for 5 minutes, okay? What I want you to think about is you're watching that after about a minute or maybe 2. I don't know about you guys, but I can see the bone scan pretty well. Like if I look at the screen, I'm like, hey, this looks pretty decent, looks pretty good, right? It's looking right. If I'm doing like a bone scan, I can see if there's areas that are increased in uptake. Maybe there's something going on in the knee joint. We're looking for a hairline fracture. I can see it. Like I've looked at bone scans after a minute, like I'm gonna go 5 minutes, after a minute, minute and a half, and the picture looks pretty good to me. Like I can look at it. Why don't I just stop then? Why do I need to wait the 5 minutes? If I can see it, why not just move on and get faster throughput on my patients?
Because the more counts you get, the more accurate the pinpoint of what you're looking at will be.
Yeah, you're exactly right. And that's what I've been trying to kind of prove this whole time with these statistic principles. I realize it's a long way to get there. But again, as I said in this last slide, when we went from 100 counts to 10,000 counts, our error went from 20% error to 2% on 2 standard deviations. The cardiologist, or well, in my case, cardiologist, but the radiologist that is reading your scan is relying upon you to get enough counts that his statistics are correct, so that when he reports that I'm doing this to 2 standard deviations and therefore with 95% confidence I'm reading this test, he doesn't know. I mean, they can look at how many counts you use, that data is on there, but the only way he has of guaranteeing that it's accurate is if you get enough counts. Again, with nuclear medicine, it's random, right? It's random. Even the way we gather data is very random, and it's not perfect. We can't perfectly measure and create everything because of that random nature of radioactivity. But if you get the accurate amount of counts, then we know statistically that we can prove that we're at a very, very low percent error. Now, what's cool about this is 10,000 counts, and you're talking about a 2% error. If you then took this up at 2 standard deviations and you said, okay, well, we're not talking about counts, we're talking about hundreds of thousands of counts, right? Like you might on a bone scan, you're doing to 500,000 counts or whatever, right? You're doing way bigger than that. Take that math and do it there, you're gonna get down to like 0.2% error, 0.02% error. Okay, so it's going to go really small. So what we're saying is that we have a the more counts you get, the more that you have data that we can predictively rely upon for the radiologist to be able to say, I'm reading this and I'm accurate. Okay, that's how we can guarantee the accuracy of what we do. That's why it's important. And I've seen techs do it before. I've seen techs throw something on the camera and they're like, oh, we're supposed to wait until we get 750,000 count range, but whatever, it looks good, let's just move on, right? Don't do that, because when you do that, you're making the report that the radiologist is doing technically inaccurate, right? And the way that we can guarantee we're doing good, accurate work that is accurate and correct is to get enough counts. That's why protocols are set up for a time or a count base, is that's how you can guarantee the accuracy of your images. And the only real way in nuke med, because of the nature of how nuke med is we can only do that with statistics. Okay, on your boards, they're not going to have you figure out percent error, but there might be general principles that want you to understand why you need to get counts, why you need to have enough counts, and how that affects the read of the image. Okay, so that's why. I realize it's a long discussion to get to what seems like a small payoff, but that's why we care about our number of counts in nuclear medicine. So again, I'm gonna give you one thing from last time and this one. These are kind of the two, like, this will make you a better tech. The one I said last time, please get your detector close to your patient. Again, I understand that there's reasons you can't do it sometimes because of patient habitus and claustrophobia and whatever. So you're gonna do the best you can for your patient to get through the scan, but get that detector as close. That makes you a better tech because you're gonna get better images, okay? This is the second one. Count and do enough time for what your protocols say, because this is the reason you're doing it. Don't try to short out. Now, again, just like with the other piece of advice, you're gonna have times where your patient can't tolerate it or whatever, and it's fine. You can cut the exam short. We'll get what we can get and get a diagnosis, and that's okay. But be a good tech. Get your camera close. Count for the number of counts that you're supposed to count to. This is the only way you can tell if your stuff is actually accurate, statistically speaking. Okay. Let's see. A couple other things I need to show you. So this is the standard deviation of a series of counts. Okay, and they use this when they start measuring the accuracy of your machine. So a physicist will come in, and what they'll do is they'll put a source on your camera and they'll measure sets of data. So they'll count your camera for 5 minutes and they'll do that multiple times. Okay, so they'll end up with a series of numbers that they want to get a standard deviation on. So this equation is what they do for that. And again, you won't need to know this, but I'll walk you through it real quick. It's just plus or minus the square root of the summation of the number subtracted by the mean of all those numbers squared divided again by the number. Okay, so it's the mean divided, or the summation, the number you're using divided by the mean squared divided by the number. Don't worry about it. But essentially this is how they do it. So if you were to look at an example of this, so this is like if a tech came in and they measured and they did 10 measurements. Here's the counts they got off of each measurement. So this is like on a camera, right? They got this amount of counts each time they did the measurement for a certain amount of time. They figured out the deviation and the square of the deviation. When you do all that math, I actually did the math over here. You come up with plus or minus 485. So in this case, your physicist that would come in and your equipment itself would have a certain range of standard deviation that it wants you to be within. Okay, so let's say your machine said your counts can't deviate past a standard deviation of 500, and let's say your physicist came in and they did these numbers. This is what they got. They did the math and they got plus or minus 485. So they would be like, okay, we're within the standard deviation. That means the system is able to count and accurately count on this system. And that could be your camera, that could be your thyroid probe, it could be anything that you use to detect radiation. Again, is they're going to use statistical analysis of counts to determine if things are accurate and correct. Okay. The other thing that is listed on your boards is something called chi-square. And in the several years that I've done this, I've tried to find what they ask you about chi-square. And when I've tried to distill it all down, they just want you to generally know what chi-squared is and what it's a measurement of. So I'm going to explain to you that really quick, tell you what you kind of need to know, and then we'll be done after that. So chi-squared, what chi-squared is, it's a measure of counting machine accuracy. When I say counting machine accuracy, I mean not the entire camera, but whatever the electronic side or the circuit or whatever it is in your camera that is the actual counter. This chi-squared test measures that. Okay, and what they do is they do the data the same way. They'll do observations with numbers of counts, but the equation is slightly different. It doesn't have a square root in, so it's still the summation of the same thing we talked about over here, divided by, again, it's not divided by the number, but it's divided by the mean. So it's a little bit different. But essentially what happens is you end up with a number at the end. In this case, with this data, I just ran it through and I got 298.65. Then what happens is there's something called a chi-square table. And there's actually one in the back of your Waterstrom book. In the 8th edition, it's on page 632. And what you do is the physicist will do the measurements and then he'll go to a chi-square table. Down this left side is the number of times you did the measurement, okay? And then there's a table, and I won't get into where these numbers come from. It's based on a bunch of physics that we don't need to worry about with counting physics and machine counting. But essentially you go down and you find, in our case, in the last slide, we did a number 10 measurements. So you go down and find the 10 column. And then what should happen is that your accuracy, if you're between 0.1 and 0.9 and you find your number there, then you're going to be accurate. So here's 0.1, or here's, let's see, there's 0.9 right there. So if we're in between, or excuse me, 0.9 and then 0.1, sorry, 0.1. So between 0.9 and 0.1, these two, if you're anywhere within those numbers on the amount of measurements that you did, then you'd be considered accurate. So on our data that we have, we go down to the 10 and we go over to 0.1, we're at 4.87. If we go to 0.9, we're 16. We got 298.65. So that means the counting system in this data is way off. So something's wrong here, it needs to be fixed, okay? Again, you won't be doing this, you won't be doing this data, but that's what the physicist is doing when he comes in, is he's taking that equation, doing a set of counts, and then comparing it to the chi-squared table to determine if it's within those ranges. Honestly, all I really want you to know about chi-squared, because again, it's listed on the boards, is I want you to understand that it's a measure of counting accuracy, machine counting accuracy. Okay, chi-squared is a measure of machine counting accuracy. Just put that in there in your head, and I think that's the basics that you need to know. And I put that in the slide here, so you can kind of look at that. Let's see, we already did that. I don't think we need to go over this again. That's just the difference between standard deviation and chi-squared. We kind of covered that with all that I've said, so I'm not gonna worry about that. Last couple of last slides I'll throw up here. Anytime we get errors in our imaging, again, radioactive decay is a random process, so our diagnostic quality is going to depend on those number of counts. The way we can guarantee, because we only have statistics to use, is number of counts collected, the fact that your machine is reproducing correctly. So that's the two things we kind of learned about in our statistics. And then of course, there's always human error, right? We can always make mistakes in what we're doing, but that's kind of where most of the errors come in nuclear medicine. And then the last thing, this is just listed, it's in your book that they want you to go over. I couldn't find a good place to throw it in, so I'm putting it in here. But they talk about the difference between when we do a diagnostic test, we call tests, how sensitive is our test and how specific, the sensitivity and specificity, what's the difference between those? The way the book defines them is that sensitivity identifies the probability that you do a test and it's a positive test, okay? So it's the percentage of fraction of patients who have something, and then you can detect that something. That is how sensitive your test is. Then the specificity is the probability of negative tests, meaning the percentage or fraction of the patient who is well and then has a negative test saying they're well, okay? I don't know what kind of questions you'll get in terms of boards on this, but it's included in your chapter and talks about it under statistics. So I'll just throw it up there. That's it. Any questions? If not, like I said, I'll make sure your test is up by Monday. Let me stop my sharing here so you can see you guys. I'll make sure that the test is up by Monday. I'll review it so that hopefully we don't have any errors like we did last time. And it'll be accurate for you guys. And then again, I had a couple of questions also on test corrections and when they're due by. I did not put due dates on your test corrections. I want you to just be able to work on those as you can and as you have time. If it were me and you guys, if there's an ideal situation, I would do those test corrections before I kind of move on to the next section that you're studying, just because then you kind of wrap up what you missed and kind of complete that learning curve before you go on. But I understand right now your lives are crazy with schools and clinicals and everything, and a lot of you are probably working too. So I remember crazy days. So I didn't put a due date on those for that reason. So don't stress about due dates on those. Other than that, check the syllabus for the next time that we're meeting. It's back to our normal schedule. It'll be on a Thursday again, and that will be our last one. We'll be covering PET CT, and we'll cover kind of CT and PET at the same time, and then we'll be done. You guys will have made it through your first semester with me. So, any other questions before I let you go?
Hey, I have a question real quick.
Yeah.
On my exam, I actually had the same question asked to me about 5 or 6 times. Like I had about 5 or 6 duplicate questions on the exam.
Really? Was it the exact question?
Yeah, the exact question. It did, the multiple choice answers were in a different order the second
Really?
time it was asked, but I just wondered how we could fix that because
Yeah,
most
no,
of them
that's
I
not,
got right, but one of them I got wrong. So I was
yeah, no,
penalized
that's,
twice.
oh my God, I'm so sorry. So, yeah, so to kind of give you a little more detail on the difference this year is in the past, I had tests and those tests were set. And what I could do is grab a test and move it to the next year and then update it or whatever. And what it did this year, they changed the Chi tester a little bit to where it makes me do a test bank. And what I have to do is I have to tell the system, okay, I want you to take X amount of questions from the test bank. But what I do to make sure everybody gets the same questions, or at least I thought, was that I give you, if the test bank has 50 questions, then I tell the test, please give this student 50 questions. My understanding of that was that it should just give you each one of those 50 questions. But now having told me that, I'm gonna have to look into that. And I'm sorry. I will go over everybody's test and correct weird errors. I did not anticipate or see this coming. So I'm gonna have to
Was I
probably
the
call
only
somebody.
one that had-
What's
I
that?
just wondered if I was the only one that had that issue. Did anyone else have
I'm gonna
duplicate
bet
questions?
you're not if you had it.
I also had it.
Oh, gosh,
I did as well.
I did as well.
I'm gonna have to call somebody then and find out why it's doing that to me. I am so sorry. Dang it.
No problem.
I'll go through them and take a look. I'll make sure that grades are looking good because that's my bad. I gotta find out why it's doing that. I've never had it do that before. Oh,
How many questions were supposed to be on the exam?
I think I ended up with 35. I'd have to look.
Okay.
Let me here. I can probably pop in real quick.
Well, the amount of questions was like 45, and maybe that's
45, I
why
can't
it
remember.
needed 45, and you only had 30 something, so it just had to duplicate some of them.
That's interesting too. I wonder if that's why it's trying to duplicate it. It's trying to see more questions than when I entered it, according to what I thought anyway, I entered the amount of questions that's in my bank is the amount of questions I put on there, but maybe something went weird. I'm gonna look into that too. Thank you. Maybe I'll check those number arrangements. Oh, sorry. I will look into that and try to find out what the heck is going on. And I'll try to figure that all out by Monday so that the next test doesn't mess up with you guys. And maybe with that first test, we'll just give everybody a good grade and move on. I'll decide. I'll figure something out. I apologize. Any other questions?
That would be. Thank you.
You guys wouldn't
Yeah,
be against everybody getting an A on the first test? All right, didn't think so. Of course, there's probably one of you that's like, I got 100%. That's not fair. No, just kidding. Okay, any other questions? All right, I will let you know what I found out. I'm gonna go ahead and end since we're a little past time. You guys have a good one. See you next time.
Bye. Thank you.
Thank you.
Thank you.
Welcome.